When I push on an object, why does it move? It took humans a long time to figure out that it moves because of forces. What is a force? A force is something that will change the motion of an object when not resisted. And these forces cover many of the things that we've observed in our universe. But for this video, we're going to use forces to prove the conservation of another entity known as the conservation of momentum. Before we can prove the conservation of momentum, we need to know some calculus. Calculus is a branch of math, but how can we define what math is? Generally speaking, math is the study of rules that are always true, and calculus is the math of change. Now the specific part of calculus we need to know is differentiation. I'm going to teach you how to apply differentiation and what it means, but not how to prove that it's true. That will be out of the scope of the video today. I want you to imagine if you had a ball in the air like this. What would happen next? The ball would fall because gravity is pulling on it. This is a very specific statement about the ball, but it doesn't have to be the ball. Any object will fall back down to ground due to gravity, whether it's this elephant or this guy. There is a more general way we can say things fall. Things fall because they have weight, let's call it W, and objects on Earth have weight because of mass, which is the amount of matter something's made out of. We're going to call that M. Objects have weight because the mass wants to accelerate towards the Earth, which I'm going to call G. So weight is the mass times the acceleration due to gravity. To understand why it's multiply, you can watch my previous video which I linked below. These symbols have given us a general purpose formula, and this formula shows how the variables affect the final result. So weight is affected by mass and acceleration due to gravity. How does it apply to differentiation? Well, using differentiation in physics, we don't want to know the specific way something changes, we want to know the general way something changes, and that's what these symbols allow us to do. It gives us the general ways of change. Let's say I want to differentiate this formula to find out how the weight changes with mass. We give that this symbol. The lowercase d means small change, so dw means small change in weight, and dm means small change in mass. Wait, why do we divide the small change in weight by the small change in mass? To answer that question, we need to know what it means to divide anything. Take the example of speed is equal to distance travelled divided by time taken. To know how fast something is going, its speed, just knowing the distance travelled is not enough. We need to know the distance an object travelled, confined to or covered in the limit of the time taken for it to travel there. And that's what the divide is for. It's saying that the speed is equal to the distance travelled confined to the amount of time it took. This doesn't just apply to this formula, but all other formulas you come across in physics. Pressure is equal to force divided by area simply means that pressure is when force is confined to a particular area. Can you guess what density equals mass divided by volume actually means? It means density is when mass is confined to a particular volume or space. So dW by dm means the small change in weight confined to or covered in the limits of the small change in mass. And here's how we work it out from the top formula. First, we identify what's changing. Well, we want to know how the weight changes because of the mass, so that becomes dW by dm. What else will be changing? The mass will change, but the acceleration due to gravity, that will remain fixed. That won't change because of the weight or mass. Now that we know what's changing, in this case mass, step 2 is to write the power next to that thing that's changing. Now there are no powers on the mass, but anything to the power of 1 is itself. So we can pretend there's a power of 1 on the mass. The final step is to times and take. So 1 times m is m, and taking 1 from 1 will be 0. Anything to the power of 0 is just 1, so it's 1 times g. dW by dm is therefore equal to g. So in summary, the small change in weight confined to a small change in mass is equivalent to the gravitational field strength. Let's use this to prove the conservation of momentum, which will appear in things like general theory of relativity and quantum mechanics. Those are for later videos. For now, let's prove the conservation of momentum. The conservation of momentum says that for a closed system, a system where we account for everything that exerts a force, the total change in momentum with time is 0, and since it's not changing in time, it's conserved. Let's prove this. Imagine a few point-like objects. They could be planets or something else. Now let's name them to remember them. I'm going to name them 1, 2, 3. Let's consider the forces acting on the system. The force on object 1 would be equal to the force on object 1 due to object 2 plus the force on object 1 due to object 3. Think of plus as unify. If you unify force on object 1 due to 2 and the force of object 1 due to 3, you get the total force acting on 1. What about the force on object 2? Well, that would be the force on object 2 due to 1 plus the force on object 2 due to 3. Finally, the force on object 3 would be the force on object 3 due to 1 plus the force on object 3 due to 2. Now, if you worked out the total force, which is F1 plus F2 plus F3, you'd see all of them cancel out and the total force is actually 0. This is because of the commutative and associative property in mathematics, which you can search on your own time, but briefly speaking, it means if you added something like this, the order in which you add doesn't matter, it gives you the same result. We already said the total force is equal to 0. How do we use this to prove the conservation of momentum? Well, again, in the previous video, we know that force is equal to mass times acceleration. Acceleration is just how velocity changes in time. We can write that as dv by dt. Plugging this definition into the top formula means that mass times dv by dt is equal to 0. Momentum is a measure of an object's motion, and it's given the symbol ρ, which looks like a p. And by definition, it's mass times velocity. There is also the commutative and associative property of multiplication. Using this, you can rearrange the formula m dv by dt to be d by dt times mv. mv is equal to momentum, thus we can replace the symbols mv with just the symbol of momentum. Perfect. Now this formula is saying that the time derivative of momentum is equal to 0, which means that momentum doesn't change in time and therefore is conserved.